In this module, we will be talking about the applications of HMO theory with particular reference to cis and trans-butadiene. The n-pi star and pi-pi star transitions of formaldehyde will also be discussed. Learn about the application of HMO to the pi-pi star transitions in trans and cis-butadiene. You will also learn to apply symmetry to predict the selection rules for the transitions and the application of group theory to predict whether the possible transitions of formaldehyde are allowed or forbidden. Use of symmetry and application of HMO theory gives a value for the pi-pi star transition wavelength, which is slightly longer than the observed value as we had seen for ethylene. This success of our approach prompts us to investigate the effect of conjugation by studying the conjugated double bond system butadiene, which can be considered as formed from two ethylene molecules. The selection rules for n-pi star and pi-pi star transitions will also be deduced using group theory. So, first we will discuss the pi-pi star transitions in trans and cis-butadiene, and we will see that different rules are predicted for the two isomers. The butadiene molecule can exist as the trans or the cis isomer. There is an S-trans structure and there is an S-cis structure. The two isomers belong to different point groups. Trans belongs to C2H and cis to C2V. As you can see, we will first consider the trans isomer and find out the selection rules. How do we put it in a Cartesian frame? We will put the 2pz orbitals house the electrons that become part of the pi framework, because it belongs to C2H symmetry. There is a center of symmetry, there is a plane and there is a C2 axis. The C2 axis will obviously be the Z axis. The next important axis is the one that defines the plane, so that will be the Y axis, and the 2px orbital will be perpendicular to that. The molecule is in the xy plane and the electrons are perpendicular to the plane, that means they are in the 2pz orbitals. The pi electrons will be in the 2pz orbitals. The character table for the C2H point group has E, the identity operation, a C2 passing through the center of the 2 carbon 2 carbon 3 single bond. They will be at the center of this perpendicular to the plane of the molecule. This is a C2 axis. I is also passing through this point, the center of the 2,3 single bond, and sigma h is the molecular plane, which is the xy plane, and these are the different symmetry elements. And when you apply the various operations on the 2pz orbitals, chi1 will be the 2pz orbital on carbon atom 1 and chi2 on carbon atom 2 and so on. When you apply the different symmetry operations, you find that there is no effect with E, because that is the identity operation, but when you perform the C2 operation, which is passing through the Z axis, chi1 becomes chi4 and chi4 becomes chi1. Sign does not change because it is the 2pz axis. I will change the sign also, exchange chi1 and chi4 and also change the sign of the orbitals, and sigma h is reflection in plane. So, chi1 will remain in place, but its sign will change, and similarly chi2 will also show similar behavior. Chi3 and chi2 and chi3 exchange, and chi1 and chi4 exchange positions under some of the operations of the point group. And when you add up the different results, you find that the reducible representation has a character 4 for E, 0 for C2, 0 for I, and -4 for sigma h. When you apply the reduction formula, you find there are 2 AU orbitals and 2 BG orbitals. And when you apply the projector operator method, as you had done for ethylene, and you apply it to the first row, it gives you psi AU is equal to chi1 plus 4, and when you apply it to the second row, you find psi AU is equal to chi2 plus chi3. Similarly, for psi BG is equal to chi1 minus chi4 and psi AU is equal to chi2 minus chi3. So, you can assign the irreducible representations to the MOs using their symmetry properties. Without even doing an HMO calculation, you know that the number of nodes in the wave functions is n minus 1 according to the particle in a box model where n is the MO number. So you look at this, you will find that there is 0 node for the n is equal to 1 orbital. For n is equal to 2 MO, there is 1 node, 2 nodes for n is equal to 3 and 3 nodes for n is equal to 4, and the energies after the HMO calculation are alpha plus 1.618 beta, alpha plus 0.618 beta, and the antibonding orbitals are alpha minus 0.618 beta and alpha minus 1.618 beta. We note from figure that the two opposite carbons chi1 and chi4 have same signs if there is an even number of nodes and opposite signs if there is an odd number of nodes. Thus chi1 and chi3, where the number of nodes is 0 and 2, they will transform as Au, and chi2 and chi4 will transform as Bg. The ground state configuration will therefore be 1 Au twice, 1 Bg twice, and since everything is completely filled up, the electronic state is a singlet Ag state. When you excite an electron from the HOMO to the LUMO, you get an electron configuration 1 Au2, 1 Bg1, 2 Au1, and there are two spin states which are possible, singlet and triplet, and hence Bg into Au is equal to Bg, and the two states are 1 Bg and 3 Bg. You get two states, one singlet and one triplet. The singlet triplet transitions, as you know, are forbidden, but the 1 Ag to 1 Bg transition is allowed, and xy in plane polarized because x and y together transform as Bg. Of the other single excitations that are possible, psi2 to psi4, psi1 to psi3 and psi1 to psi4, only the last is allowed, and this is also xy polarized. The other two are 1 Ag to 1 Ag, which are Laporte forbidden. Only the last is allowed by the electric dipole selection rules, and it is xy polarized. Then we will see whether cis-butadiene has similar selection rules or different ones. Now this belongs to the C2H point group, and here the different operations are E, of course. C2 here is passing through it is in the molecular plane and at the bisection of the 2,3 single bond, and so this is labeled as Z. And similarly you have a sigma xz which is perpendicular to the plane of the molecule, and then there is another reflection plane which is the plane of the molecule, and this is sigma yz which is the plane of the molecule. So since the molecular plane is yz and the pi electrons are formed by linear combinations of 2px orbitals because they are perpendicular to the plane of the molecule. So these are denoted as chi-I as we have been doing previously, and when you perform the various operations on the atomic orbitals, you find that chi1 under the operation E remains chi1, but C2Z it becomes minus chi4 because this is a reflection in the Z direction and the molecular orbitals are in the X direction. So it changes sign and also exchanges position with chi4, sigma xz chi4, sigma yz will also be minus chi1. So when you add up all these, the reducible representation is 4 for E, 0 for C2, 0 for sigma xz and minus 4 for sigma yz, where it is reflection in plane. So all the orbitals change sign but do not change their position. So when you resolve this, what you find is that you get 2A2 plus 2B1, and when you apply the projection operators, you find that for A2 chi1 minus chi4 and chi2 minus chi3 combinations lead to A2, and for B1 the combinations are chi1 plus chi4 and chi2 plus chi3, and again we go back to our figure, we see that chi1 and chi3 transform as B1 and phi2 and phi4 as A2. The ground state configuration of cis-butadiene is therefore B1 twice, A2 twice, and it is a closed shell singlet 1A1. The first excited state gives rise to the configuration phi12, phi21, phi31, because one electron is promoted from the phi2 MO to the phi3 MO, and that means that the new electron configuration is B1 twice, A2 1, B1 1, and product A2 into B1 is equal to B2. So there are two resulting states, one is 1B2 singlet state and the other is a triplet state 3B2, and when you look at the C2V character table, we see that the 1A1 to 1B2 transition is allowed and it is Y polarized because behaves like B2, The 1A1 to 3B2 transition is of course forbidden by the spin selection rule, because there is a change of spin multiplicity in this transition. Then you consider the other single electron excitations, Psi2 to Psi4, Psi1 to Psi3 and Psi1 to Psi4. They are 1A1 to 1A1, 1A1 to 1A1 and 1A1 to 1B2 transitions. They are all allowed, and all single electron transitions are permitted by the electric dipole selection rules for cis-butadiene, because there is no center of symmetry and so no Laporte selection rule. Trans-butadiene, for which some of these transitions were forbidden by the Laporte selection rules. This rule does not apply to the cis isomer which lacks a center of symmetry. Now we come to the transition energies. For both we found that the HMO transition was allowed, and we want to find out, because this is the longest wavelength transition, what is the transition energy. When you apply simple HMO theory, you can apply the same secular determinant is there for cis and trans isomers, because HMO theory only looks at the connectivity and not the orientation of the orbitals. The topological matrix HMO is given like this: wherever there is an atom we put X in the diagonal, and wherever there is a bond between 1 and 2 we will put 1. Where there is a bond between 1 and 3 there is no bond, so we put 0, 1 and 4 there is no bond, and similarly we can fill up the rest. And when you solve this 4 by 4 determinant, you get the eigenvalues plus minus 1.618 and plus minus 0.618, and X in this case is equal to alpha minus E by beta. It follows that the orbital energies are given by EI is equal to alpha minus Xi beta. The HMO transition energy is thus from alpha plus 0.618 beta to alpha minus 0.618 beta. The difference is minus 1.236 beta, and again we take a value of minus 2.4 electron volts for beta, and you find that the transition wavelength is equal to lambda is equal to Hc by delta E, and this is equal to 418 nanometers. Again this does not agree very well with the experimental value, which is 217 nanometers. We can blame this discrepancy on the uncertain value of beta. Studied the pi star transitions, we now want to see whether we can predict anything about n pi star transitions, and we take the simplest molecule having non-bonding electrons, and that is formaldehyde. And we take up this molecule formaldehyde, which also has non-bonding electrons on oxygen. It is like ethylene, but it has oxygen instead of one CH2 group, and see there are non-bonding electrons and how they affect the spectra. To construct the molecular orbitals, we need only consider the valence, that is the 2s and 2p orbitals on carbon and oxygen, and the 1s orbitals on the two hydrogens. The core oxygen orbitals 1s, and for carbon also the 1s, they are too deep down to make any contribution to the electronic spectra. The oxygen 2s orbitals are also very low in energy, and they may also be considered as non-bonding, because they are oxygen is very electronegative, and so it has very low lying orbitals, and that is why the 2s orbital can be considered as non-bonding. All the s orbitals transform as the totally symmetric A1 representation of the point group of the molecule, that is C2V. The core therefore comprises 1s on oxygen, which is 1A1, 1s on carbon, which is 2A1, and 2s on oxygen, which is 3A1, and we will be ignoring these core electrons, but they will only help us in counting the orbitals. The next orbital in order of energy is the carbon 2s orbital. Carbon is bonded to oxygen by a double bond, and it is singly bonded to the two hydrogens. Since the molecular plane is YZ, carbon can form single bonds using orbitals in this plane. These are the 2s, 2py and 2pz orbitals, and from the C2V character table it is revealed that these transform as A1, B2 and A1 respectively. It is clear that the sigma bond with oxygen is formed by overlap of the 2pz orbitals, and the pi bond by overlap of the 2px orbitals of the two atoms. This leaves the 2s and 2py orbitals of carbon for bonding with the hydrogens. To understand the bonding with hydrogen, let us look at the behavior of the two hydrogens under the operations of the C2V point group. The two hydrogens, they exchange positions under some of the operations. For example, if I label one of the hydrogens as HA and the other one as HB, under the E operation HA remains HA, but under C2 operation it transforms to HB. There is no change in sign because it is spherically symmetrical. Similarly, under xz it exchanges position and becomes Hb, and under sigma yz it becomes equal to Ha, and similarly for Hb, and that means that the reducible representation has character 2 for E, 0 for C2, 0 for sigma and 0 for sigma yz. Now when you analyze this, you find that the two irreducible combinations are A1 plus B2, and when you find out the corresponding linear combination using projection operators, you find Ha plus Hb is for A1 and for B2 it is Ha minus Hb, and these linear combinations can then bond with carbon using the 2s and 2py orbitals of carbon respectively. To enable bond formation, the electronic configuration of carbon is now changed to 1s2, 2s1, 2px1, 2py1, 2pz1. Oxygen bonds with carbon using the 2pz orbital for forming a sigma bond, because this will be in plane, and its 2px orbital for forming a pi bond. In order to form these bonds, the electrons are arranged as 1s2, 2s2, 2px1, 2py2, 2pz1. Since there are no available electrons in the 2py orbital of carbon to bond with oxygen, the 2py2 electron pair on oxygen is non-bonding. And very nicely this is shown in this figure, that these are the bonding orbitals and this is the anti-bonding orbital. Where there is overlap, there is delocalization, that is a bonding orbital, and where there is no delocalization, you find that it is an anti-bonding orbital. And so we can arrange the orbitals as such. The lowest energy orbital is 1s oxygen, followed by 1s carbon, then 2s oxygen, then sigma 2s on hydrogen, sigma 2py on hydrogen, sigma on carbon oxygen bond, pi of carbon oxygen, then non-bonding on oxygen, then the anti-bonding pi CO orbital, and then the anti-bonding sigma CO orbital, and we put the symmetries, and as usual the lowest energy one is labeled 1A1, the next one is 2A1, 3A1, 4A1, 1B2, 5A1, 1B1, 2B2, 2B1 and 6A1. The CH sigma anti-bonding orbitals are very high in energy and we have not included in the list. Now let us see what are the possible excited states. Simplest excitation is from the highest occupied level to the unoccupied one, and this we will see corresponds to an n pi star excited states. There are a total of 16 electrons in formaldehyde which occupy the first 8 MOs, resulting in a ground state electronic configuration 1A12, 2A12, 3A12. We fill up the electrons according to the Aufbau principle until we reach 2B2 electrons, and since they are completely filled up, the non-bonding NO 2B2 MO is the HOMO and the anti-bonding pi star 2B1 MO is the LUMO. So the ground state is 1A1 and I have written X bar. The longest wavelength transition results from the promotion of an electron from the non-bonding 2B2 MO to the pi star 2B1 MO, and the excited state electronic configuration will then be, the rest is the same, 1B1 twice, 2B2 1, 2B1 1, and from this two states arise. One is 3A2 and the other one is 1A2, because B2 into B1 is equal to A2, and there are two unpaired electrons and they can give rise to either a singlet state or a triplet state. And you notice that I have written something like A bar and A capital bar. These are known as n pi star states. It is also clear from figure that the n orbital 2B2 is not a pure oxygen state. So when you actually do a calculation, a computational calculation, you see that orbitals of the same symmetry will mix. So although we are calling it a non-bonding orbital, it has some contribution from sigma 2pYH, which has the same symmetry 1B2. Also sigma star orbital 6A1 is also mainly sigma star C 2SH, and these are the various orbitals that we have obtained using a computational calculation, and you can see that what you predict and what you actually observe is slightly different, and these are the energy levels of formaldehyde, and we have shown in particular the n pi star transition. And what is the non-bonding orbital? It is not entirely oxygen, you can see, and the pi star orbital also what kind of anti-bonding orbital it is, you can see. The yellow and blue colors, you can consider one of them as the positive lobe and the other color as the negative lobe. The n-pi star transition is however forbidden by the electric dipole selection rules, since no component of the dipole moment transforms as A2, because when you take the product, the excited state is A2 and the ground state was A1. No component of the dipole moment transforms as A2. Therefore, it is not an allowed transition, but again you do observe it, and this is at around 285 nanometers for formaldehyde. Now we consider another excitation, and that is from the pi level to the pi star level, and this is called the pi star excited state. And this is the other important transition, and here promotion of an electron from the bonding pi state to the anti-bonding pi star state takes place, and it results in the electronic configuration. Everything else remains the same, 1b1 1, 2b2 1, 2b1 1. The resulting states are 3a1 and 1a1, and these are known as pi star excited states. The transition is allowed by the electric dipole selection rules, and it is Z polarized, since Z transforms as A1. Hence it is very intense, and it is much more intense than the forbidden n-pi star transition, and it involves higher energy because n states are higher in energy as compared to pi states. So the n-pi star transition has a shorter transition energy as compared to pi star, and so the pi star transition occurs at shorter wavelength at around 187 nanometers. And here you can see pi star is at a lower wavelength and it is more intense. N-pi star is at a higher wavelength and it is less intense, and this is the general behavior for all molecules which have carbonyl bonds. Two other possible transitions are n to sigma star and sigma to pi star, and they result in excited state electronic configurations 1b1 2, 2b2 1, 2b1 0, 6a1, and the other one is 5a1 1, 1b1 2, 2b2 2, 2b1 1, and the states that you get are either singlet or triplet B2 or singlet or triplet B1 respectively. Sigma to sigma star transition we are not considering, it is from 5a1 to 6a1, and it results in singlet and triplet A1 excited states, but we do not consider because it involves a very large amount of energy and is usually not observed. All these transitions are allowed by the electric dipole selection rules. It is observed, but in the vacuum UV region, and we have already discussed it is very difficult to study sigma star transitions, so we do not consider them. Hence, there are 4 transitions which are important for this chromophore, the carbonyl chromophore: n-pi star, pi star, n sigma star and sigma pi star. The HMO transition involves transfer of the in-plane non-bonding oxygen 2py electron to the out-of-plane anti-bonding CO pi star orbital. This n-pi star transition is characteristic of carbonyl, C double bond S, N double bond O, NO2 and ONO chromophores. It is one of the most important electronic transitions and occurs in the range 353 to 230 nanometers. So, we will summarize what we have learned in this module. We have learned that group theory can be used to label the MOs of butadiene, cis and trans, and to determine whether a transition is allowed or forbidden. All transitions are allowed for cis-butadiene, but some are forbidden for trans-butadiene due to the Laporte selection rule. HMO theory can be used to predict the transition energies. For formaldehyde, the n-pi star transition is forbidden by the selection rules, but it is observed and it is an important transition, and the other pi star transitions and n sigma star transitions are all allowed.